Okay. There's a few announcements first. Due to a problem with the room booking, because what we're going to do is we're going to do digital assessment. We'll be using Exemplify software for our midterm. And there was a problem with the room booking, so the UG office actually booked the room for me at 1 to 3. Our lecture is from 4 to 6. So in the end, all the rooms between 4 to 6 are already booked. So the only way we can have a midterm is if it's on a Saturday. Okay, so we will have our midterm on Saturday of week 8. It's 20%, and it will be at U-Town Auditorium. I believe it's U-Town Auditorium 1. I will post this slide later as an announcement. Okay, so that's the bad news. The good news is that because our midterm is already on a Saturday, I'm going to cancel our makeup lecture because we have 2 public holidays on Monday. The second public holiday is Deepavali, which is on week 11. Okay, so I'm going to cancel that. The rest of the schedule are still the same. The other thing is that now, because of these changes, we will need to change our lecture schedule. This is the updated changes. The few things that you need to take note here is that next week we will start with a briefing. Okay, so NUSIT will come down here to give us a short briefing on how to use Exemplify. This will be between 4 to 4:30. And then we continue on with the normal lecture. Okay, and because of the room booking problems, I'm just going to move up. So this component in red here was previously in week 9, 10, and 11. I just moved it up by 1 week. Okay, and we will not have a make-up for week 11 lecture. Okay, so any questions on this? Okay, so there's changes that we will have during the course of the semester. So now we can continue on with the normal lecture. Okay, so hopefully you all have already read on the light introduction, because we're going to continue on from there. If you haven't, there's a recap here about the history of relational data model. First is that what you need to note here is that data is actually modeled as a relation. And what is important here is that these values, each one of these values, is not technically a student, because a student is basically the entire human being, but it contains all the information that you need to model a student. Okay? So we cannot store an actual student on a database, but what we can store is a model of it. And that's basically true for whatever it is you're doing in CS. You're only modeling real-life problems. And this is a distinction that you need to remember. So if a student only contains the student ID, the name, the birth date, and the cap, then you can store a model of it inside a table. Okay, and the second thing is that unlike a set, a tuple here is positional. The position of the values is important. If you are looking at a set, 2 sets, A, B, and C, as well as another set containing C, B, and A, these 2 are equivalent. So we can say that these 2 are equivalent sets. They contain exactly the same members. But this is not true for a tuple. In a tuple, A, B, C is not equivalent to B, C, A. because the position matters. You compare it position by position. All right? Okay, so that is basically the quick recap from the previous lecture. The overview for this current lecture is that we're going to discuss three things: the relational data model, integrity constraints, and relational algebra. We're not going to touch on SQL first. We're going to touch on the logic behind SQL. The first one is the relational data model. It continues from the previous lecture. So we know that data consists of a tuple, okay, and the tuple contains values, and every value must have the corresponding domain. What we mean by domain is that there must be atomic values, and atomic means that the value of a particular row inside a tuple cannot be another tuple. Tuple is not atomic, which means that I cannot have things like this. Okay? Because this is non-atomic. Okay, atomic means there's only a single value. String, even though you can think of it as a collection of characters, we consider it to be an atomic value. Okay? So yeah. So you cannot have tuple, you cannot have set within the domain. There is a special value called null. Okay, this is very important. It basically just means that the value is not applicable or is unknown. And the way you can memorize this is that there's this famous picture, which is this. Okay, one of them, you don't have any value at all. The other one, there is a value, but you cannot use it. It's not applicable to be used. Okay, and the knowledge of null is actually very, very important, because recently there was an article at Wired. You can try to follow this. You can try to read it. It's a very nice thing to read. It is very relevant in database. So some guy trying to have a null as a vanity plate, and basically all null values corresponds to his vanity plate. Now if there is a particular parking ticket that somehow the police officer didn't register any plate number, it goes to him. Okay, so that's basically the hell that he landed on. Okay, so in your database design, hopefully you will not get this problem. Okay, this is something that you need to take care of. Okay, so that's null. We will look at more details about null in the next week lecture. Yeah, and how null can be operated and what operations can work on null. Okay, so to continue on, so that's domain. The other thing that we need to know is relations. So again, we said that relation is basically captured as a table. So that table that contains rows and columns, we can also define it as a set. It's a set of tuples. Okay, so remember, tuple is positional, set is non-positional, which means that if I have two tuples, the way I arrange it, the way that tuples appear, does not really matter. Okay, so it will be still the same relation, even though the tuples are out of order. But the elements within the tuple cannot be out of order. And then we have a quick example over here. So if you look at this, is our example schema. Quickly look through it, then answer the following question: what is R? Then you can do kind of mapping. R is here, and this is students. So yeah, R must be students. Okay, now the convention that we use is that if it's somewhere along the line of there is a mathematical notation or it involves a heavy mathematical jargon, I will just write it out in green. Right? And for those of you who are not familiar with those mathematical terms, I will usually give examples. Okay, it is easier if you deal with examples. Okay, so now the first attributes here which corresponds to A1 is basically just look at the position. The first one is the student ID. Okay, and then you can fill in the rest. Basically what you will get is something like this. The relation name is students. The first attribute is student ID. Second attribute is name, and so on. But to define relation, it's not enough to just look at the attributes. We need to also look at the domain. Okay, so the domain, we can specify what the domain is. And because tuple is positional, we can give the position as a subscript. The attribute number I will have a domain is di. Okay, so that's how we will specify which of these attributes and what are the domains. And for this one, it's also quite easy. What you have to look at is the second half of the attributes. This is how we specify the domain. Okay, and as you remember, integer, string, and numeric have already been given as a possible domain. Now you have one more, which is the date. Okay, so if you try to fill this in, the first domain will be integer, second one will be string, third, which is date, and the fourth is numeric. Okay, so any questions so far? Okay, so after we define what is a relation, we can further define what is an instance of a schema. Okay, so instance of the schema is just a collection of that. It's a relation. Okay, and this is how we define it. Okay, it's pretty complicated. If you're not familiar, can be quite complicated. So let's look at it one by one. The result of this, so every instance of a schema is a relation, and that relation is basically a set. How do we know it's a set? Well, if we use the curly bracket. Curly bracket denotes set. We use round bracket to denote a tuple. Okay, so an instance of a schema is a relation, and a relation is a set. What is being contained within that set is tuples. Okay, so this is a tuple because we start with a round bracket, ends with a round bracket. And what this vertical line specifies is the condition to get that tuple. Okay, so first it consists of a tuple, and how many elements are there in the tuple? You just look at the subscript. There are n elements. Okay, for simplicity, I will start with 1 instead of 0. If I start with 0, then the last one will be n minus 1. Okay, so I will usually start with 1. Okay, so it's a set consisting of tuples of n elements. Now, the other thing is that the vertical bar specifies the condition, and the condition only mentions that each of the element, so each ai over here, where I can be substituted with 1 to n, is within the domain. This is a set inclusion. Alright? So this is what we have. So that's a relation. A relation is an instance of a schema. A schema is kind of like your template for a table. Okay, so it's a set consisting of tuples of n elements, where each element is within the domain. Okay, and then it's always good to have an example. This is a possible example. Okay, 2 possible tuples. And then it is within a set. Now again, I need to stress that because this is a set, if I reverse the order, which means if I have things like 3, 1, 1, 8, 1, 4, 2, 3, it is still exactly the same relations. It is still the same instance. Alright? Because as a set, the order does not matter. Okay, so any questions on this? Now once we describe what a relation is, we can also describe what is a relational database schema. Now we look at the database itself. We don't look at a particular instance of it. The database consists of multiple tables and is basically a set of schemas. Okay, so this is a possible schema, a possible schema, a possible schema. If you have a set of this, that means you just have to put this inside a set. That's a relational database schema, right? And also implicitly there is a data constraint because we specify it when we specify the schema. Okay, if the domain is implicit, or we just say that the domain are all integer, then you can actually ignore the domain. For simplicity, usually for exam, we will just say that all the domains are integer. So I can write things like okay, name is quite stupid to have it as an integer, but let's say okay, name, fine. Okay, I mean, assuming that the domain is obvious, or I say that all the domains will be integer. Okay? So this is what a relational database schema is. The relational database is, again, then, is a collection of tables, or as we say, it is an instance of that schema. So each one of this, each table consists of a is here is a set of relations. Okay, so that's what a table is. It's a set of relations. A tuple is a single row within the table. Every element within that tuple kind of part of your column. Okay, so you have rows and columns. Every tuple is a row. Okay, so you have a set of those, which means you have multiple rows. So this is an example of a relational database. And this satisfies the previous schema, which is this. Okay, so the student, I'm just going to give an instance of it. For the courses, I'm just going to give an instance of it. And for enrolls, I'm just going to give an instance of it. Okay? So any questions? Now that we know what a database is, we can look at something more. Rather than just describing it as this collection of values, of data, we can find meaning as a relationship between the values. So what kind of relationship can we get between these values? It can be described as what we call as an integrity constraint. Okay? So the data cannot be just any kind of data. For instance, if you look at your metric number, if that is your student ID, not every number can be used, or not every collection of those strings can be used as your metric number. It must start with an A. It must contain 8 digits. And then the last character must satisfy what we call a checksum. Okay? So there must be some kind of integrity constraint for it to be a valid data. So this is what we are going to describe. We're going to formalize this. So yeah, so it's basically just a condition that restricts what kind of data you can put in. Okay? So your tuple cannot contain literally anything. It must be restricted. But once it cannot contain another tuple. Okay? And we define what is a legal instance. So a legal relation must satisfy all the integrity constraints that you specify. And the good thing about the DBMS is that it enforces this integrity constraint. So if you look at your database, once you have set it up, whatever you put in will always satisfy whatever integrity constraint you put. You can never get any data that does not satisfy your integrity constraint. If you can, then you can submit a bug report to the developer. Okay, so you look at the types of integrity constraint. Okay, so these are the types. We have already talked about domain. Okay, we know how to specify a domain constraint, and that is when we talk about a schema. You have R, you have A1 with the domain 1 here, A2 with the domain 2, and so on until you have AN with the domain N. Okay, so that's how you specify the domain constraint. These are your domain constraints. Okay, but for the rest, we need another way to capture that. We will look at key constraint, but before that, we need to describe some definitions. We need to talk about what is called as a super key. Okay, super key is a subset of attributes. So you know that your tuple consists of multiple attributes. You basically look at some of it, and then within that partial attributes, if you look at it, you can know what is the rest of the value. So that's what it means by uniquely identified. Now let me give you a simple example. Because the other way of thinking about what uniquely identifies means is to look at functions. If you have a function square, right here, let's call f a function square. Okay? You look at some of the values, f2. The square of 2 is simply just 4. Okay? But a square of minus 2 is also 4. If you transpose this into the context of relational database or a tuple, I can have a relation that specifies a relation R that basically says x and fx. Okay, so that's my relation. Some legal instance consists of 2, 4, minus 2, 4. Alright? Now, if you look at it, if I remove one of the values, let's say 2 question mark. Do you know what the question mark is? Right? So that's what it means by uniquely identified. Right? If you just look at the table, that means there's only one value that can correspond to this question mark. On the other hand, if I put question mark on here, can you know what the question mark is? Okay, there are two possible values. Okay, so 4 does not uniquely identify anything. 2 uniquely identifies the other one. Okay, so that's what uniquely identifies means. But you can again expand this to a different set or different tuple, which means that you can just find a corresponding functions that, let's say, binary function gxy that says x plus y. Then what you have is a tuple of 3 elements. 1, 2. I can then put question mark here. Okay? So the first 2 columns, the first 2 attributes, uniquely identify the third attribute. But any other combination is probably not going to do it for this. Okay, this one uniquely identified. Because of that special property. But okay, so this one, that's not uniquely identified. Right? So that's what uniquely identifies means. So with this example, I can give the following question: which of this is a possible super key? Now the the more interesting question is, I can give you the answer obviously, but the more interesting question is, how do we know? How do we find what is the possible super key here? Okay, we have what we assume here to be a legal instance. Because if this is not a legal instance, then we cannot say anything. Okay? We assume that this is a legal instance. Then what we can say is that, yeah, so just look at it. Look at this one by one. You look at SID. Is there any SID that are the same but give a different value on other attributes? Okay, that's what we call as a violation. So we look at this. These two are the same, but these two are different. Okay, so this cannot be a super key. So again, what we need to do is just find all the possible violations. Okay, the other possible violation is this, CID. Because you look at this, okay, and then you have two possible violations, this or this. Okay. Any other possible combinations will not give you violations. Grade here are all unique. Okay, because it's all unique, you cannot say that there's any violation. So again, the main thing here is that if you're given a legal instance, what you can say is that, well, given this legal instance, these values are not possible to be super key. The rest are still possible. So any questions? So this is the summary of that. Those two are not super key, okay? Because of the violations that we discussed before. Now, there is a property here that we can abuse. So you can see that there are three possible attributes. So how many possible combinations are there? How many possible subsets of attributes? Okay, so it's all listed there is 7. Okay, but if it's a general one, if there's n attributes, you can have 2 group of n minus 1. Okay. Now if I give n as 8 attributes, and then you try to list out everything, then that's going to be a nightmare. Okay. So the other way you can look at it is that consider this. Grade. If you look at grade, it's already established that it is a possible super key. Because anything that contains a grade is unique. So any attributes that contain grade will be a possible super key. So again, I can immediately say that this is a possible super key. And our search space is just reduced greatly. Right? So all we have to do now is check whether this one is a possible super key. And in fact, it is, because that pair is unique. Okay, even though these two are not unique, but the combination of that, a pair of it, is unique. To be a unique tuple, all the values, okay, actually some of the values must be different. Okay, so two tuples are the same if all the values are the same. So once we have a key, because you know, if you have a super key, anything that includes the super key is also a super key. So it's not really that important of a notion for us. We want to know what is the minimal of it. What is the smallest, not just the smallest, but an attribute that cannot be decomposed further. So that is a notion of a key. It is minimal. Now there's a different subtle differences here. It is minimal, it is not minimum. Okay, there's a difference between minimal and minimum. Minimal means that you cannot remove any of the attributes further. Minimum is the smallest one. Okay? What we are interested in is the minimal, not the minimum. Okay, mathematically, they are different. So because it is just a minimal, that means you try to remove any attributes one by one. If you can, and then it is still a super key, then whatever it is, before you remove that, it's not a super key. Okay? So again, you need to be careful here because this is a minimal, not minimum. So here is some of the same question again. So how do we find out which one it is? Okay, so we know that these two are not. Okay? Because we know that these two are not, and we have already established that at least these two are. Okay, so we can now say that anything that contains grade cannot be a key because it is not minimum. Okay, so you look at this. SID and grade. Right? Can you remove one of the attributes and still make it a super key? And the answer is yes, you can remove this. And it's still a super key. So SID grade is not a key. This one too, this one is not either. Okay? And then the question is SID, CID a key? Okay, and this is where the difference between the minimal and the minimum comes into play. This is a key because you cannot remove any of its attributes and still make it a super key. Okay? So yeah, if what we want to find is the minimum, then only the grade is a key. Okay, but because we are not finding a minimum, we are finding a minimal, then both grade, both number 3 and number 4 are key. Alright? Is that clear? Okay, so I repeat, you need to have minimal, not minimum. Minimal means that you cannot remove any of its attributes again. Right? So the reason why I repeat this is because it is going to be important later on, this definition. And by that time, most of you is probably going to forget about that. Okay, so based on this definition, the only two possible keys are number 3 and number 4. Right? So yeah, this is something extra. What I'm going to talk about now is only going to be used in roughly about the week 7 when we talk about functional dependencies. But it is going to be very, very good if you start writing this notation down. Because when you start your project, you will not have learned about functional dependency yet. But if you already write down the constraint as if you kind of know what functional dependency is, it will make your project much easier later on, once you learn about functional dependencies. So the notation that I'm going to use is the arrow notation. And again, the arrow notation is used because we're kind of dealing with a function. So when you look at function, like that square, it's a function that maps from integer to integer. Okay, so x is mapped to y. If you have a variable x, it maps to variable y. 2 is mapped to 4. Minus 2 is mapped to 4. And again, we can see the relationship about this between this and uniquely identified. Okay, because if we say that the student ID uniquely identifies the rest, then the student ID arrow any one of the rest is true. You can kind of ask yourself if there is a function to take things out from the database such that the student ID match something. If you have f of student ID, and f just look at the entire database and retrieve that particular tuple, you will only get a single tuple. Okay, so that's why we use the arrow notation. And if you don't have an arrow symbol, because your keyboard definitely will not going to have an arrow symbol, we're just going to use this. Okay, it's a dash and a greater than. Okay, it looks like an arrow, so that's why we're going to use it. Okay, so again, this is going to be generalized later on for lecture 7. So in general, what you will have is the left-hand side, an attribute on the left-hand side uniquely identifies whatever attributes on the right-hand side. Okay, so it's kind of like your function, and that's why it's called a functional dependency, which again you will only learn in lecture 7. But if you can identify this when you start out your project, hopefully it will make things easier when you need to normalize the project. If you do it afterwards, it may be too late. All right? Okay, so we know about superkey, we know about key. So let's talk about what are the properties of keys. When you look at the relation, it can have multiple keys. Okay, so like we looked at before, that particular instance have two possible keys, number 3 and number 4. Okay, number 3 is just grid. Number 4 is a pair of SID and CID. These are what we call the candidate keys. So candidate keys are basically a candidate for primary keys. Primary key is this very important notion in database because you can put a restriction of what a primary key is. A primary key basically identifies the tuple. And to make things easy, the database can actually check if you specify that certain attributes have to be primary keys. The database will check whether there is any duplicates of that, or if that value contains a null. Okay? So you specify what the primary key is when you create your database. How do you choose the primary key? You need to look at what are the keys available. So basically you look at the possible candidate keys, you choose one of them. And the one that you choose typically is up to you. Okay? But try to choose the one that is most logical to have. For instance, like consider a possibility that you have a car. Let's say that every car manufacturer only produces one possible type. Okay? That means a pair of manufacturer and type is a candidate key. However, there is a much better choice of candidate key, which is the plate number. Okay, so try to use the most logical one. Okay, even though there might be multiple. And to make things easy, we just put it as an underline. If the primary keys are known, we put it as an underline. Okay, so two examples there. Student ID is the primary key. The pair SID and CID are primary keys. Okay, the way you create a database with this particular primary keys will be next week. The other thing that you can restrict, so another kind of constraint that you can have is what we call a foreign key. Foreign key refers to another primary key. It's foreign to that table. So you have something, and this something refers to another table, possibly another table. So it's foreign to you. If you look at this, what we do have is actually the student ID in enroll. So if we have enrolls here, this SID, we can have a restriction saying that all the values over here must exist over here. You can only get the values that exist there. So that's what it means by a foreign key. So SID is referencing student ID. Again, the other possibility is that this one is going to reference this. Okay? The grade cannot reference the cap because this one does not exist over here. Okay? So a few terminologies. If you do this, that means the students table is what we call as a reference relation. It is being referenced. The enrolls is the referencing relation. Okay? And between the CID and the course ID is this. These are the relationships. Okay? The requirement for foreign key is that it needs to satisfy two things. One is that the value must appear as a primary key in the reference relation. Or it can simply be null. Right? You can actually have a null value, which means that you do not know where to reference yet. And this is actually important. But the reason why it is important is going to be known when we talk about ER diagram. Okay? The main idea here is that if you have a circular referencing, you can never insert anything unless you have a null value. So that's basically it. Okay, and this is a very important constraint. It can be the same relation. All right? So any questions? All right, so let's take a quick break here because we're going to look at the last. Oh, I haven't changed. The bottom one should be relational algebra. Yeah, so this is our last topic for today. We're going to take a quick break. So let's have a 10-minute break. We'll come back at 4:55. Because for audit, you just need to do any MCQ. Midterm there will be some MCQ. Then just do the MCQ. Really? Okay, then you probably need to. Okay, so then we just arrange. Yeah, I need to double check with the deans of the city. But if you do need to have a project, I'm just going to do all of the auditing. There's enough for one. So, yeah, so that's probably what I'm going to do if you are required to do it. Yes. Oh, okay. Because from what I know is that the minimum is that you need to do MCQ. It could be the same way because you're referencing yourself. Preferably not. But okay, so let's say you have. Let's say you can have this referencing this. This is a primary key. You can do that. Yes. But if you reference your own attributes, you can never insert anything there because nothing is going to be there at the start. Either that or it's just trivial, right? It's either trivial or you cannot put anything there. No, it's not. I mean, you reference your own attributes, yes. But if it's you reference your own table but different attributes, it can be useful. Like you can have a table that consists of the mentor and the mentee. mentor must exist, mentee might not exist. You might not be mentoring anyone. But if you are mentoring someone, then someone must exist as another mentor. Cool. Yeah, or the schema itself, because the number of attributes in your relation and the schema attributes. Yeah. No entry as well. So the thing is that those are possible. It's not, it may not be correct, but those are the possible superkeys. Yeah. So there are two ways to look at it, right? When you look at the legal instance, you know these are possible. But if you already know that these are the constraints, then you can generate all the possible or you can generate all the possible relations. Yes. Yes, the instance. Yes, roughly yes. I mean, the way we use it is typically interchangeable because unless there's only one key, then no, so unfortunately I don't really think I can help because it must go through the VG office. That I'm not sure because currently the VG office is getting swamped by requests. So there might be some backlog. Yes. I'll try to. Okay, but by the time we finish this lecture, they will already be closed. I'll try to go to them tomorrow. Again, don't get your hopes too high because from what I heard, they're getting swamped. Yeah. All right. Settle down. Okay, so the next part of our lecture, this is louder. Okay, the next part of our lecture is going to be on relational algebra. So, what is relational algebra? So it's simply just a formal language, and you can use it to actually ask something about relations. Okay, again, remember that relations are your legal instances. So this is how can you retrieve things from there, how can you modify the instance, the relations into another relations, such that you get what you want. It's composed of relational operators, and there are two basic relational operators, the unary Unary means there's only one input, or binary. There's two inputs. Now if you talk in terms of functions, then the unary is basically R to R. You have a relation, and then you output another relation. The binary operators is basically R and R. You output a relation. Right? And there's a lot of binary operators in comparison to the unary operators. What we're going to use here is actually a subset of it. If you look at the reference book, so because we're not going to use it, they actually have a lot more operators, but we're not going to go into that. This is what we're going to use, and we're going to introduce a few more later, well, in subsequent lectures. Okay, so the important thing is that it outputs a relation. The input, one relation or two relations, and then you output a relation. So we work on this example database with some example foreign key constraint. Okay, you have pizza, restaurant, customers, and what the customer likes, what the pizza contains, and so on. And these are the example database. Okay, because of the, oh, it's actually still quite visible. Okay, it's kind of pretty small on my screen. But yeah, because it's, especially the contains, there's a lot of it, so I have to make the font smaller. So let's start with the simple one, the unary operators. There's a few. The basic one is what we call a selection. Selection basically filters out everything that you do not need. And the way you specify it is that there is a condition here. The condition is written as a subscript. So that's the condition. The original relation before you perform the selection is specified as the input. Right? So again, you can see that it is a function that takes in a relation, and what it gives you is a relation that contains anything that does not. What you get is everything that contains. What you get is a tuple that satisfies the condition, right? So that's what you get. The input is a relation. The output is a relation such that all tuples within that relation satisfies the condition. Now, if you're familiar with Python, this is basically your filter. And the name itself is weird in a sense that once you learn about SQL, SQL has a keyword called select. And unfortunately, select does not correspond to the selection. Okay, so this is something weird. Okay, and what can you write as a condition? What can you write as a condition is mainly Boolean. Most of the symbols are the same. So if it's equality, you use this. if you check whether x is equal to y, where y can be a constant or another attribute, this one, the way you write it is, if it's not in a mathematical form, is actually this way. Okay, less than greater than. So if you say x less than greater than y, means that x is not equal to y. Okay, so again, this one is also just separate, and also this one. Okay, the rest are quite standard. This cannot be written. So for that, you just say and, or for this particular one, it's not. Okay? So yeah, and there's operator precedence, but if it's not clear, what you should do is just write brackets around terms such that it's clear. Right? So if you're not exactly sure if what is the operator precedence for this, then just write brackets around whatever it is to make it clear. Alright? So that's what I'm trying to do as well. So as much as possible, what I'm going to do is I'm going to try to make the bracket there such that it's clear what is the meaning. Okay, so it's always good to have examples. So the first one here, let's say we have an example table there. The way it works is that you filter out what you do not need. So let's say you have a condition. The condition is C. For each of the row, you check whether it satisfies C. If it does not satisfy, you don't include them. So there's a, you just cross it out. Now whatever remains must satisfy C. So that's what you get. Alright? So this is what you get. Okay, the rest can still be, the rest there might be other things. So that's why I put it as a dot dot dot. Okay, so any questions? So this one remove rows, and if you work with Python, this one is better known as a filter, especially if you have taken CS 1010S. So a possible example is this. You want to find all restaurants, the pizzas that they sell, and their prices, such that you want only all the prices that are under $20. Okay? So how do we solve this? Well, the condition that you need is that the price is under $20. So then your C. Your C is equals to price under 20. Okay, and then you need to figure out which table you need, which relations you need to select this from. Okay, and there is actually a table that contains all this information, and the table is the cell table. So what you can write is, this is a lowercase sigma. So sigma with the price less than 20. So you want to select everything with the price lower than 20 from the cells table. Right? So this is what you get. So if that is the formula that you give, that is the function that you want to run, given this particular table, all you have to do is erase everything that does not satisfy the condition. This, erase, erase, erase. So what you will get in the end is Corleone corner with Margherita with a cost of 19, and Gambino oven with Siciliana, and Pizza King with Diavola. Okay, so that's what you get. So you first check whether any of this satisfies the condition. For those that satisfies the condition, you keep. For those that does not satisfy the condition, you remove. And at the end, you just simplify it to be this. Okay? So, any questions? Okay, so let's have another example. The other example is more complex. We want to find all the restaurants, the pizzas that they sell, and their prices. So again, we need to look at the sales table. But now our condition is two things. One is that either the price is under $20 or the pizza is marinara, and the other condition is that the pizza cannot be diavola. And the answer to this is, actually I read it as a wrong thing, but let's look at it first before I modify it. The first part of the condition, this is condition number 1. The price is under 20, and the pizza is marinara. Now what is wrong is that this one should be this. Okay? Should be and instead of or. And yeah, and the pizza cannot be diavola. Okay, so let's correct this. That's a wedge. Okay? There's a lot of things to correct over here. Okay, so any questions? So you look at the condition first. You have two conditions. This is the first one. This is the first condition, and this is the second condition. Okay, and then you break it down. This condition 1 and condition 2 must be valid. Condition 1 contains two subclauses. It's either the price is under 20 or the pizza is marinara. Okay? And again, if you write it as an SQL statement, what you will get is this one will be this, and this one will basically just say and this one is basically just say or. Okay? Because the keyboard does not contain those special symbols. Okay, so any questions so far? This one is less than, greater than. Huh? Yeah, it's not equal. Okay, so any questions? The next unary operators that we're going to look at is the projection. Projection is basically you remove columns. And that's it. What you specify here in this list are the list of columns you want to keep. You can do some kind of reordering with this if you want. Which, let's say for this, between these two, what you want to keep over here is just the R name and pizza. Okay? So if you want, you can write this as pi, R name, and pizza from cells. If you want to reverse the ordering of the tuple, then you can actually also say pizza and R name. Then you need pizza first as the first column and R name as the second column. Okay, you can do a little bit of reordering over here. Okay, so it's not simply just removes columns, but you can also reorder. This is kind of like your map in Python. So if you think about map and filter, this is map. Selection is filter. And so it may happen that once you remove a certain column, there may be duplicate records, duplicate tuples. Okay, it's not in this particular instance, but if we look at, okay, so this is the answer for the find all restaurants and the pizzas that they sell. You basically just get the pie with the appropriate list of attributes. What I want to show next is if removal of a column results in a duplicate, then what you do is you also remove duplicates. Okay? Because again, it's a set. Relation is a set of tuples. Set cannot contain duplicates. So this is an example. If you simply remove the R name, the intermediate value that you have will contain north, central, central, south, and east. But the central, oh, so this one is gone. The central is duplicated. So you just remove them. Okay? And the answer to this is you get the projection. Projection is pi. So projection, and all you have to do is project only the area. Okay? But it just so happened that by projecting only on the area, you encounter a duplicate. This central will be duplicated. So you just remove one of them. Okay? Any questions? And that's basically your projection. The last unary operator is what we call a renaming, and it's using the symbol rho. So this is the Greek word rho. You basically just take the first letter. Selection is sigma, projection is pi, renaming is rho. When you rename, you can rename a few things. The first one, you can rename the schema, which is the table name over here, can be renamed. The attributes can also be renamed. All right? So that's basically just renaming. You have R, A1, A2, AN, you have S, this is renamed to this, renamed to this, renamed to this, renamed to this. The number of rows and the number of columns are unchanged. And also you cannot reorder the columns. The reordering is from pi. And when certain things are clear, let's say you just want to name, you just want to rename the table. You do not want to rename the attributes. Then you can just specify the table name or the schema name. If you just want to rename the attributes, just put a bracket and list all the attributes. Okay? Unfortunately, you have to list all the attributes, even if you want to rename only one attribute. Okay, if there are like n attributes and you just want to rename one, the simplest way you can do that is by saying that row A1, A2, and then you have BI, and then until AN. You have to specify the rest. They are still unchanged. All right? So any questions? So now here, in the example, restaurant is going to be renamed to shops. The restaurant name is going to be the shop name. So our name is going to be S name. The area is going to be a region. Okay, so you can see that we want to rename everything. So we have row, shops, as name, region, from restaurants. Okay, so that's the unary operations that you are doing. And that's basically this. Alright? Okay, so renaming is actually the easiest, and the use of it is mainly optional. Okay, unless the question says that you need to give these specific attributes, most of the time you don't really need this. So that's basically it for unary operators. Any questions first? Yes. There won't be duplicates. All the rows are unchanged. Only the column name. Okay, and you cannot rename it such that two columns becomes the same name. Okay. So you must make sure that the column name will be unique. The data here are unchanged, so there need not be any duplicate removal. Right, so any other questions? Okay, before we move on to the binary operation, because binary operation requires you to give two relations, we need to define something first. This is what we call the union compatibility. Okay, so this is quite a mathematical definition, but it basically just says that they must have the same number of attributes, and each attribute must be the same domain. Okay, you cannot have a mismatch attributes. That's basically what this is. So an example. Consider three cases, and then which one of these are actually valid binary operations. Okay? To be valid, it must be union compatible. Okay, so you look at this. Students and grad students. Even though they look similar, but students contains three attributes. Or the way you look at it is just look at the types. You have int, date, string. For the grad student, what you have is int and string. So immediately you can see that these are not matched. So they are not union compatible. And also student and report. Student and report, you see there's integer match, but the date does not match the string. Okay, so this one, again, is not. Once you do a projection on the student, you have SID and name only. So once you do the projection, the left side will be integer and string. And the right side, which is the grad student, is also integer and string. So they are union compatible. So this one is okay. Now the last one is where I say that the projection can be used as a reordering. Here you have SID, name, and date of birth. So SID is an integer, name is a string, date of birth is a date. And if you look at report, report is integer, string, and date. Okay, so they are union compatible. Yes. Then no. Yes. Because numeric may not be convertible to an integer. Numeric contains floating point. Right? Okay, so any other questions? So that's union compatibility, and we need this. Because otherwise you cannot merge the two. You cannot union the two tuple if they are not union compatible. But if they're union compatible, the intersection is definitely going to be union compatible. And the set difference are also going to be union compatible. So those are the two values, the number 2 and number 4. And then we can now look at the 3 possible binary operators first. So we look at the cross product later. Union is easy. Union, that means you look at the tuple that exists in either one or both. You just combine them. Intersection, they must exist in both. Set difference, it exists in R but does not exist in S. Okay? Out of all this, set difference is non-commutative. So union, this is the same. This is the same, but this one is not the same. Right? And then we require all these 3 to be union compatible. The last one, cross product, we don't require it to be union compatible. Okay, so let's look at the simple one. This union, the example is that we want to find all customer and restaurant names. So we have restaurant, we have customer, but this one is R name, this one is C name. So which one should we use? Okay, so what you can do is you can rename one of them. I choose to rename this to R name. Or you just choose, in any case, you don't even have to rename it. It will just follow the left-hand side. Right, so what you need to do is just project. Because you do not need the area. So what you can do is you can remove the area first. If you remove the area from both, then they are still union compatible. And then you just union them. Okay, so the removal of this area is basically a projection of R name on restaurants. And this one is the projection on C name on customer. And then you just union them. Okay, so that's one possibility. The other possibility is that you can actually union them first and then remove area. We can do that in this particular instance because both are still union compatible originally. So you can do R name on R union C. All right, we just assume that the attributes on the left hand side is going to be used as the name on the right hand side. Okay, so this is what you will get. That will be the formula. This is one possible example. The other possible solution will be the one that I wrote before. R name of restaurants union customers. Right? What this also shows is that the relational algebra is not unique. You can have 2 different relational algebra expression that equates to the same thing. Alright? So yeah. So any questions on this? The second one is intersection. So this is intersection. It must contains both. So what we can do is we can ask, find all pizzas that contains both cheese and chili. So we try to find an intermediate table. The intermediate table is this contains only cheese and this contains only chili. And from here, we perform an intersection of that to get this. Okay? To get everything that contains cheese or everything that contains chili, you need to use selection. And then you do projection so that you remove the ingredient. Alright? So that's how you can solve this. This part, you select first everything that contains chili, and then you project such that you only have the pizza name. For this one, you select everything that contains chili. So this one cheese, this one chili, and then you project on the pizza name. Okay, and then to get this table, you just do an intersection. All right? So any questions? So the last one is set difference. Pretty much similar, but it's a different kind of question. It contains cheese, but not chili. Okay, the intermediates are all the same, but the last one, instead of doing an intersection, what you do is you do a set difference. Okay, to get this, it contains cheese. You do a selection and then projection. This one is chili. You do selection on ingredients of chili, and then you do a projection. And then to get this, you do a set difference. Okay, so that's what you have. Any questions? Okay, so the last operator is kind of big. This is the binary operator of the cross product. Okay, so this one is pretty complicated. So we look at this. What does it mean? What it means is basically you combine the two tuple. You combine the two tables such that you get all the possible combinations. So every instances of this, every instances of a tuple from R1 is combined with every instances of tuple from R2. Okay, so let's say we have 0 and 1. And this one is 1, 0. And then the other one, so this is A and B. The other table we have C and D. We have 0, 0, 1, 1. A cross product of this basically contains 0, 1, 0, 0. Okay, so you take from here, you combine with this, and then you take from here, you combine with this. You get 0, 1, 1, 1. And then you do the same. This combine with this, so you get 1, 0, 0, 0, and then you get 1, 0, 1, 1. Then you get A, B, C, D. Okay? And this is the reason why you don't need union compatibility. Because the result is a different relation. Right? So any questions? Yes? It doesn't matter, right? Then what you do is you rename the first column first. One of the columns, basically. In any case, foreign key doesn't require you to have the same column name. Remember that W actually is a where was it? When we talk about foreign key, okay, so the CID is a different column name than the course ID. So your foreign key does not require you to have the same column name. Okay, so you just basically merge everything. This is also what we call a Cartesian product. So one possible question that we can ask you is that find all the customer restaurant pairs. They are located in the central area. Okay, so what you can do is you can find all customer in central. You can find all the restaurants in central, and then you do the cross product. That's one thing that you can do. Okay? The other thing that you can also do is you can do the cross product first, and then you select that the customer is in central and the restaurant is in central. Okay, whichever one that you feel is more reasonable. Okay, but if we follow this idea, we can then separate the each of these statements into different operations. To find all customer in the central, what we can do is we can say that there is a relation R1 that we can obtain from this. We do a selection such that the area is within central. And we get that from the customer table. And then we do a projection such that the area is removed, so that we don't have duplicate column. To find all the restaurants in central, again we can do selection. Right? So once you have that, you have these two relations. You just do a cross product on it. The problem with the cross product is that if you think about it logically, this table is going to be very, very big. The number of elements here is the number of elements on R1 multiplied by the number of elements on R2. Okay? Luckily for us, this one is actually pretty small. Okay, but you get what it is. You get this one is 2, this one is 2, the size of this is 4. There's a possibility that you can get something that is very, very large. However, because we're talking about database, it's the job of the database to make it computable. It's not your job. Yes, you have. For this particular question, huh? So again, what's so for this module, we don't care. We don't care about the time complexity, right? Because that really depends on whether your DBMS is optimized for that or not. Okay, if you want to know more about it, you can take the 3233, I believe, the database implementations. So yeah, in our case, as long as you get the result correct, we will accept it. It doesn't matter how you do it. Okay, so that's a cross product. And then this is a property that we can abuse. So remember that the input to any of the operations are relations. The output are also relations. We have what it calls a closure. Closure means that the input and the output give you exactly the same set. So this is an example. A positive integer, so z plus, is closed under addition. If you have addition, if you have 1 plus 2 is equals to 3. The result will be a positive integer. Any positive number that you choose, if you add them up, the result will be positive numbers. Okay, but it is not closed under subtraction, because 1 minus 2 is not a positive. Okay, there is a kind of a closure in this relation, and that is that unary operators are relations are closed under unary operator, and relations are closed under binary operations. We can kind of represent that as a diagram. So this is the input relation. If you do any one of these operations, what you will get is another relation. If you have any one of these operations, then you need two input relations. So what does it mean? Closure is something that is very, very nice because you can chain operation. Remember, we did that before, right? You have phi of something on sigma of, so this one is L, sigma on something. You can do this because this produces relations that can be used by this. Okay? So that's what it means by closed under this operation. And that means that we can chain. The advantage of chaining it is that we can compose relational algebra to form what we call a relational algebra expressions. Okay, but this one can be complex. So what we also want to introduce to you is the diagram. You can put it as a diagram in the sense that you can draw it as something like this. This is the customer. The customer, if you use a selection operation, you get this. Okay, you give it to the operation above it. And then the output of this, you can give it to the pi operation. Right? And then you can also do the same for the other one. You can get this. And then from here, you can give it to the cross product operation. All right? So if you are not exactly sure on how to write things, you can actually draw the diagram first. The diagram make it clear which order you should apply things. All right? So yeah. Lastly, we have a possible questions for relational algebra. This is a typical questions. So find all customer pairs C1 and C2 such that they share a common pizza. And then you must order them such that C1 is lexicographically smaller than C2. Okay, so you have this likes. Lisa and Maggie has the same likes, both like Fung Hee. Lisa and Mo also, Maggie and Mo. Okay, you want to get all of this. So how do you get what is R? Well, first you need to cross product likes with likes. So now you get the double the likes, and then you can select everything such that they have the same like. Right? So what you can do is you can do a cross product. Once you get the cross product, you can select such that they share the same pizza. If they share the same pizza, you need to also order them. And then you project. Okay, but this is kind of too complicated. So what you can do is you can write it as a diagram, or what we can do is we can break it down into smaller queries. So this is our original R. We break it down to smaller queries. We draw a diagram, but if your drawing is not exactly good, you use what we call a sequence of steps. We did this before also. We can say that, well, the first part of this is to have this relation. The second part is then to have this relation. And the answer is the cross product. So this is what we did before. Okay? And if we look back at this particular instance, we can then say that, well, we look at the inner one. We say that this is R1. Right? And because this is R1, I can erase that and then say that this is R1. Now R2 is basically this, including R1. But you operate on R1. So that's what you get. You operate on R1. Okay? So then you can rename them as R2. And then you look at the one outside, this will be your answer. Your answer will be just the projection on R2. Right? So if you feel like it's too complicated, you can break it down into smaller steps. So yeah, so that's basically how you can break it down. And this is the other part where I say that it can be larger. Okay? The intermediate one can be larger. So this one, there are 7 here. So if you do a cross product, what you will get is basically there will be 49 of this, which is 7 times 7. Okay? So, but in our case, we don't really care about the complexity. As long as you can get the final result correct, we don't care how many intermediates, what is the size of the intermediates. So this one is 49 rows. Okay, so that's it. Any questions? Okay, so if there's no questions, then I'll see you next week. And I believe the next class is already kind of here, so we may have to evacuate the room. If you still have any questions, we can discuss outside. Sorry. Yes. Oh. I usually finish earlier, but because last week was yeah, I usually finish at